Okay, so I think we should start. Yeah, we don't have all the students, I think, in the class, but we have most of them. Some students may be at very different time zones, and so it could be very late or very early for them. But for the most part, most of you are here. So welcome to 10701. The first and hopefully last time we are doing this online, or at least fully online. This is obviously a very unusual circumstances. For some of you, this is also the first class you're taking at CMU. So welcome to CMU more generally, and of course to computer science and to this first class that you're taking. You know, it would have been, of course, much better for us to see you in person, but due to the circumstances and the fact that this is a very big class, we are doing this online. TED 701 is, you know, a very long-standing class in machine learning. It's been taught, I guess, for 20 years. Of course, it's changing as machine learning is changing, but we're always excited to teach it to a new set of incoming students. I think it's a very useful introduction to machine learning for those who have not seen machine learning. And even if you took machine learning related classes, I think you will find some new ideas and some new concepts in this class. So I'll be teaching this class together with Eric, who is also on the call. I don't know if he wants to say hi before we start the lecture.
I'm the only guy waving hands, so it's me.
And yeah, and I'll start the lecture, and then we'll talk a little bit about some procedural issues related, of course, to the class, but also to how we are going to do it over Zoom and all the other things. So let me start. Hopefully most of you were able to. Okay, so most of you were able to at least access the Piazza pages for the class where this lecture is already posted. And more generally, going forward, we are going to post lectures, the lecture slides before the lecture, so you don't need to take notes or make any copies of the slides. All the slides will be available to you before the lectures. You can, of course, annotate them if you wish during the lecture, but you will have access to them before the class. So this is, as I said, 10.7.1 Introduction to Machine Learning. The reason I'm crossing out deep neural networks is not because I wanted to say that deep neural networks are not important, and in fact, we are going to talk about deep neural networks, but I do want to emphasize, and this is something that became more important over the last 2 years, that machine learning is not just deep neural networks. There are other things in machine learning that have been very useful and remain very useful, that do not use neural networks or deep neural networks, including a lot of methods for classification and regression that can use neural network, but sometimes neural networks are not the best approaches, and other methods for unsupervised learning, for modeling uncertainty, for modeling probabilities, and so forth. So those who just heard about machine learning through deep neural networks hopefully will find some new and interesting other directions in this class. Although again, neural networks are very important in machine learning, and they become more and more important. I just want to emphasize that this is a more general introduction, and we'll try to expose you to a lot of different areas. I'm saying this because, you know, as I said, 701 has been taught for many, many years. If you took machine learning, I think 20 years ago, then the thing that you were most excited about, and the things that the people were talking the most about, was something called graphical models. So Bayesian networks, hidden Markov models, these were introduced more or less 25, or at least gained popularity 25 years ago. And everybody thought that this will solve all the problems related to representation and understanding and use for computation. So if you took machine learning 20 years ago, you would say deep neural networks. Then a few years later, there was something called support vector machine and kernels, which were all the rage. Everybody was very excited about them. They seemed to be much better at classification and doing things that we couldn't do with any of the other methods. So again, if you took machine learning 10 to 15 years ago, you would be most excited about supposed virtual machine. Nowadays, we are back to neural networks, which were actually introduced, as we will show you, in the 60s, but very slowly gained popularity and became much better over the years until 10 years ago, when they were really when a breakthrough was made. So the reason why we don't just talk about the thing that works the best now is because you never know what will be the best or potential good methods in 10 years from now. So it's good to get a very general, I think, overview of the current directions in machine learning, even if some of them may not seem to be the most popular or the most active. And then, going forward, of course, you can decide to specialize in one of them. But I think it's very important to get a broad introduction to machine learning, which is what we are trying to do with this class. Okay, so this is just an overview of how we think of introduction to machine learning. Now, in terms of a bit more technical details about the class itself, most of the information is provided on Piazza. We also have a website here that basically duplicates Piazza. The website is primarily intended for people who cannot access the Piazza pages. So if you have access to the Piazza pages, I encourage you to use that. Don't rely on the website. The website is intended for people who are watching this class from the outside and maybe not registered or maybe cannot access our Piazza pages. But generally speaking, the information that you would need as student registered for this class is on Piazza. As I mentioned, there's two instructors, Eric and myself. TAs I will mention in a second, but we also have their information, or we will have their information on Piazza, including email addresses and information about office hours. Now, this, of course, year is very unusual. In the past, we would just publish office hours for different TAs and for instructors, and you can come to the office hours, stand by the door, or TAs usually held office hours in open spaces, and you would just come and sit with others and walk and talk to them during the office hours. This year, of course, it's very, very different. Each of you, so I want to make sure that people understand. So we have two classes, which are Monday and Wednesday at 11:40. We are also going to have a general recitation for all students. It doesn't matter what office hours you're listed to or recitation slot you're listed to. All students will have recitation online on Friday between 11:40 and 1 p.m. So 11:40 to 1, Monday, Wednesday, and Friday. Okay, this is online lectures. Office hours, in-person office hours, are by assignment only. You cannot come to office hours you're not assigned to because of course, of limitations related to the in-person issues. So each of you, or at least most of you, maybe some people who were just admitted from the waiting list have not been, but each of you has been assigned an office hour slot. This slot, and some of them are actually over the weekend, I know that. These slots are for in-person office hours. You do not have to come to them, obviously. So even if you are assigned to an office hour at, I don't know, Saturday 1 to 2, you definitely do not have to come. But if you do want to come, you can only come to the one you are assigned to, and there will be a TA that you can talk to, of course, with all the restrictions, masks, and we will, of course, restrict the number of students attending. Okay, so this is the organization of office hours. In terms of Eric and myself, for now at least, I think we will do it by email. So if you want to talk to us, email, and we will set up a Piazza meeting. We can also do like a Piazza room, but the problem will be to set it up such that we have only one person at a time, and that's usually an issue if you don't schedule it in advance. So email us, and we are more than happy to talk to students over Zoom for now. So that's basically it in terms of the class organization, recitations, and office hours. Any questions on this? This is important to get it clear, because again, this is the first day of the first semester that we're doing online. I'm sure everybody has questions. We also are not completely sure about everything, so we can try and answer as much as we can. But if people have questions about this, this is a good time to ask. Maybe we can answer to the best of our knowledge. I don't know if anybody has. Oh, I do want to say something about, so we just discussed it before the lecture.
Someone just asked, do we have online office hour options? We will absolutely be hosting online office hours as well. Yeah.
Great. So in terms of questions, yeah, by the way, if you have questions, first of all, we really want to encourage people to ask questions during the lecture, especially when we have a Zoom lecture. It's very hard to get people engaged. So we do want you to ask questions. However, of course, this is a very large class. So if people start unmuting themselves and asking questions, it might cause interference. So the procedure we will go by is the following. If you want to ask a question, please raise your hand using the Zoom controls which you have in the participant panel. Should be able to raise your hand. And then one of the TAs or Daniel, which we'll talk about in a minute, will call on you and then you can ask your question. If you are worried about internet connection and you cannot ask your question, you can also write your question to the chat and one of the TAs or Daniel will ask the question for you, but I would prefer that you ask it yourself. So if you can raise your hand and ask the question, that's the best. Be prepared to wait a few seconds or a minute until someone calling you, because when Eric and I teach, it's hard for us to see people who raise their hands because we usually are more focused on the slides, so we need the TAs, and that may take a bit of time. But that will be the procedure. Let's at least start with that, and go on. Sometimes I will close the slides and move to this type of presentation, which means that I want you to ask. So in that case, I can be more concentrated. If someone raises their hand, I can actually say, yeah, go ahead. But in most of the time when we are on the slides, we would need to raise your hand. Okay. Yeah, so just the chat is filling up. I don't know if we want to. Yeah, so online office hours, we will send information about it later. Okay, let's not. Okay, so this is. Okay, so this is some issues related to organizational aspects. In terms of the class, as I said, this is the class that I'm teaching with Eric Singh, and we have introductory slides on each of the lecturers. I actually don't have one for myself, but I'm Ziv Bar Joseph. I'm a professor in the machine learning department, computational biology department, and my work mainly focuses on using and developing machine learning methods for the analysis of biological high throughput data. So data about events happening in our bodies and inside our cells. I'm co-teaching this with Eric, who, as I said, is online. Eric, you want to say something about your interests in machine learning? I mean,
I want, okay, it's already written here. I'm Eric Xing. I'm a professor at the Machine Learning Department and also CS and LTI. Here's my research interest. I mainly work on machine learning theory and system. And I developed some applications in the healthcare space. And recently I've been interested also in learning new topics such as auto ML, trustworthy ML, personalizable ML, and transfer machine learning. These are basically the augmentations of either existing or new algorithms, in a number of different application settings. This little graph is kind of showing you how these topics can be organized in a synergized way to solve different types of problems. Thanks.
Great, thank you. Now, so Eric and I are teaching the class. In addition, we have an instructor or education associate. The official title changes, but basically Daniel, who is also online, is in charge of all the organizational aspects of the class, including in charge of all the TAs. And if you have any issues related to scheduling, to your slots, to any other things related to personal accommodations, you can contact him and us. And he will basically, he's basically running the class behind the scenes, let's put it this way. So Daniel, yeah, so you can email or contact him for any issue you have. In addition to Daniel, or working under Daniel, we have 7 TAs. Now, this year, in the past, all TAs did everything. So all TAs did all the recitations and all the problem sets. This year, we are dividing it slightly differently. So we have 7 TAs, but you will interact primarily with 4 of them, and 3 will be primarily behind the scenes. It's good for you to know because they will be working on problem sets and exams and so forth, but you probably will mainly interact in terms of office hours and recitations with 4 of these TAs, and the other 3 are very important for the class, but you may not see them in person as much. So why is it? Why does it always? Yeah, I guess people can see it, but when I display, you don't see it, right?
Yeah, it looks to me like the image is missing, but the image is definitely there when I made the file.
Yeah, the image is missing from, let's see if I have it. Anyway, so Roger, I actually do have the image. I don't know why it's missing. You see, when I rescale it, you see it, right?
Yep, yeah, that works.
I don't know why. Anyway, this is Roger. I think he's on the call. He's a PhD student in computer science, and you know, he's interested in a few things, as you will see here, including in ML. And he will be one of our TAs, and he will, as I said, hold office hours, recitations, and so forth. Hopefully, from now on, the slides are going to work for me. Let's see. Yeah, next is Avi, who is a PhD student in computational biology. And all of these, by the way, all of the TAs took this class in previous years and have done very well. So Avi is a PhD student in computational biology and works on machine learning and personal medicine. Clay, who is a master student in language technologies on NLP and data visualization. John, who is a master student in computer science department and works on parallel computing. So these 4 are the ones you will interact with primarily. And then we have a few other TAs that are, again, working mainly behind the scenes, although you may see them in office hours and recitations. How do I, would you pronounce it, Daniel?
Hey, it's Chandri.
Chandri, okay. Yeah, okay. Chandri, who is a master's in robotics, again, working on reinforcement learning. Bhuvan, computer science department. Jay, who is working in the computer science department as well. Okay, so this is our staff. It's a big staff, but of course we are a big class, and especially this year with the way we divided the in-person hours, or the office hours, we needed a bigger staff. Okay, so this is in terms of the class staff. In terms of the class content, and this is of course very important. So the class is divided into a few different modules. The first one, or the first 2 are mainly focused on something called supervised learning, and we'll discuss what that means in a second. Next, we talk about unsupervised learning, then graphical models, a bit of theory, and then something we call actions. The first, the detailed schedule is already available for you on Piazza. These are just the dates of the different lectures. And again, the first, or at least the third of the class is going to be on supervised learning, and then the rest is going to be smaller modules on other applications. By the way, each of these, almost any part of this is just a foundation for a more advanced set of classes. So we have a full class that Eric usually teaches on graphical models. We have classes on neural networks. We have classes on optimization. So each of these lectures is only exposing you to a very brief introduction to an area that can be greatly expanded. A few key things you do, or a few key time points, dates that I do want you to keep in mind. The first is the exam. So we are going to have, and I will talk in a second about the requirements, but we are going to have an exam in this class. The exam will be during class time. Of course, it will be online and it will be slightly longer. So it will be roughly 2 hours, but it will be during class time. And it's going to be a single exam. We won't have a final. It's going to be on Wednesday, the end of November, November 23rd. And we'll talk a lot about what we expect from you for the exam and what material we're going to cover, how the exam will look like, and so forth when the time comes. But I do want you to be aware of the date of the exam, okay? So that's important. And again, it's going to be online, and we'll discuss the material for that, or we'll discuss the procedure for that. The second important date is something we call poster presentation. So the class involves the project. I will talk in a second. And you will need to present your project in a poster presentation on Wednesday. Unlike the exam, this is not restricted in time. Again, we will talk exactly about the procedure, but the basic idea is that you will record yourself for 10 minutes and upload that, and we will actually watch it during that day. But this is a deadline for recording yourself, and then you will have another deadline for submitting the write-up. So the project will be a poster presentation and a write-up. The poster presentation deadline is Wednesday. So you'll have a deadline by which you will have to upload the video, but you will not have to be, or we will not have a specific time that you will need to be present. Okay, so that's less of a restriction in terms of specific time, but it is a deadline that you need to be aware of. Now, in terms of the other requirements for the class, so you will be graded based on 3 primary tasks. One is problem sets. So we're going to have 5 problem sets. Problem sets in Introduction to Machine Learning are a major component of the class. So we expect them to be, or they are not trivial. So they will be a major, likely will be something you spend a lot of time on. So they will account for 40% of the grade, the exam will be 30%, and the project will be another 30%. Now, just to be a bit more explicit about the problem sets, so we're going to have 5 problem sets. The dates of the problem sets have already been assigned. So if you look at the schedule, you see the dates of each problem set, when it's out, when it's due. The problem sets include both theoretical and programming assignments. We have a late submission policy, which is very detailed in the, it's already on Piazza, Daniel, or if not, we are going to post it.
Yes, the syllabus is there.
Okay, so you will see on Piazza, we have some details about late submission and so forth, so just follow that. If you can submit on time, no problem, but if you need some late days, everything is discussed there. But these will be probably the most, or the thing you will work on the most during the class. So that's the problem sets. And as I said, include both theoretical and programming assignments. Project. So we have a project in 10.701. This is one of the hallmarks of a graduate class in CMU, and especially 701. We really are actually looking forward to seeing the projects. However, the projects are going to be limited in terms of the topics. So we are going to provide a set of topics between 5 and 7 topics. We haven't selected all of them. And you will have to choose one of these topics and associated data. So each topic will be a specific problem definition and associated data, and you will have to work on that specific topic and data. So for example, if it's a classification task, we may give you some images and ask you to come up with new classifiers or compare different classifiers for this specific image classification task. Usually the project involves data that is coming from research of either the instructors or the TA. So it's really state-of-the-art data, but the challenge is to see which methods can be applied to improve performance or to compare performance on the project. And again, we will talk more about the projects when the time comes. Projects are going to be in groups of 3. So we have a strict requirement that there will be 3 people. So you have to start or try to find teammates. We will definitely not approve teams greater than 3, and we will try to not approve teams with less than 3. So if you want to work on your own or with someone else, it's unlikely that we will approve it unless there is a very strong argument to why this should be the case. So groups of 3. I always tell students, working in groups is something that you should expect. I know that in undergraduate it's unusual, but from graduate level going forward in industry or in academia, even if you do PhD research, in most cases you are not working on your own. You work with other people, collaborators in groups. So working in groups is something that you should get used to, and you might as well get used to it as part of this class. As we said, as I said, there is going to be a poster session, which will be recorded, and a write-up. We will give instructions, detailed instructions about both later in the class, but generally speaking, the write-up is going to be like a journal paper, 8 pages, including references, and you will get specific templates and all instructions later in the class. Exam. So Daniel, I see that people are posting to the chat. If there's any question, you can stop me and ask. Okay. Right, exams, as we said, a single exam. Yeah, it's probably not going to be in the afternoon. So this was, so you can ignore this. The exam is going to be during class time. Recitation, as we said, every Friday, and unlike what you may have understood from the fact that you are assigned to office hours, recitation, we are going to have only one recitation, and it's going to be on Friday, including this Friday, we'll have the first recitation. And generally speaking, the recitations are usually tied to the problem set. So each recitation usually overlaps with one of the problem sets, except for the first two, where we don't have a problem set out. So the first two recitations, including the one this week, will be a background on probability and some introduction to Python for those who are less familiar with programming, okay? And generally speaking, we will hold recitations on Friday and Friday at 11:40. Now, I should say, this lecture is recorded, or all the lectures are recorded, and also the recitations are going to be recorded. So recitation, although, again, we highly recommend that you participate in person, everything is going to be recorded, except for the office hours are not going to be recorded. So this is something you'll need to participate. Okay. Good. So that's it in terms of organization. Any questions before we move on? Usually people have some questions. I don't know if I need to look at the chat or.
I've been responding to them as they come in.
Good. Any question? Any other question anybody wants to ask? Organizational question before we move to some content. Yeah, the topics for, yeah, so there's a question about topics for the project. I think we are planning in the next 3-4 weeks, right, Eric, to have
yeah, hopefully within 3 to 4 weeks. Yeah.
And again, the goal of the project is really to have you use or extend some machine learning methods. So we usually teach a bit and then show the project rather than the other way around. But yeah, you will have a broad selection. So this will cover a lot of different types of machine learning issues, ranging from classification, regression, modeling, and so forth. So you should find something that interests you in the project. Okay, more important, I think, to think about forming the teams at this stage rather than okay, good. So if there's no more questions or no more questions that I need to answer, we can move on to the content, which is okay. Okay, so one question that we often ask ourselves, and this is not, I mean, this is an exercise we are going through periodically because machine learning keeps changing. But I think the first time we really spent a lot of time on trying to answer this question, what is machine learning? And both Eric and I were part of those discussions when we first started, or when we started the first machine learning department in the US, maybe in the world, in 2007. So CMU, of course, has a machine learning department, and it emerged from a center of machine learning. And then in 2007, it became a department. And one thing that a department needs to do is have a mission statement. What does the department, or what is the department working on? And there, we really had to basically specify what machine learning is. And, you know, it's one thing to say what you are, but it's also important to distinguish between machine learning and other domains. Okay, so what's the difference between machine learning and theory? What's the difference between machine learning and statistics, data science, which didn't exist back then, and other things? So let's see at least what we think about when we say machine learning. So obviously machine learning has two parts. One is machine, so it needs to be automated, or there has to be some computation automation component. But the learning is the really hard things, or harder things to define, right? So basically, when we talk about machine learning, and there is a lot of different areas in machine learning, and I'll discuss several of them today, but generally speaking, we are looking for methods that can generalize from data. Generalize from data means that you can take data and learn classifiers, so how to predict certain things. You can learn regression, how to predict continuous values, how to predict discrete values. You can learn how to organize things using clustering. You can learn how to model things using different graphical models, and a lot of other things that you can generalize. But the idea is to take the data, and the data only represent a subset of the general space, or the overall space of things that you can see, and come up with a way to explain it such that you can generalize, you can make inference, you can make decisions based on that. Okay, so this is the general definition of machine learning. Most of what we will talk about will follow this idea, but we'll take it to different places. So either for classification, for prediction, for clustering, and so on. Okay, so generally machine learning goes along this diagram. So you have data. Using the data, we come up, or we employ a learning algorithm, and there's lots of learning algorithms, and they're doing different things. And once we have the outcome of the algorithm, we can generate new knowledge. New knowledge can mean that if we take a new sample, we can classify a new image, we can say what this image is, or maybe we can generate new samples from some music that we never heard, or maybe we can say something about the probability of an event. This is knowledge. This is things that we didn't know before, and we needed the combination of data and the algorithm in order to generate. So that's the idea of machine learning. Somehow generalize the data using some algorithms in order to create knowledge. And again, sometimes you can take it to a very extreme level. For example, as I'll show you, there are cases where people are trying to come up with methods that keep on generalizing and generalizing and getting more data. Sometimes you just want to generalize once. So basically you take a set of inputs, you learn some model, and that's what you want to use. So there could be a lot of variations on exactly how to use this formula, but more or less for most of the methods we will talk about, this will be the process. As I said, machine learning, that sounds like a good, or this idea of generalizing from data may sound like a good idea or an important idea even. And the question is, okay, did other people think about it before, or this is just a new name for something that we have been doing for decades or even centuries? For example, statistics, is it similar to statistics? What about AI, right? We often, when people talk about deep neural networks, they often talk about artificial intelligence. We usually view neural networks as part of machine learning. So what's the difference between AI and machine learning? Data mining, data science, what's the difference between all of these definitions? So sometimes I should say, I mean, I will talk about some differences, but again, sometimes people really mean the same thing when they use different words, right? So when people refer to neural networks as AI, and we refer to them as machine learning, it's not like we look at different types of methods. Both of them are using neural networks, but neural networks are really maybe the intersection of both. But there are cases where machine learning is completely separate from AI. Okay, so that's the one goal of the next slides, right? To emphasize the uniqueness, or the things that machine learning is unique with respect to these other fields. The goal of machine learning, as we said, is to improve, using methods to improve what we can infer from the data using computational methods, right? To create new knowledge. And if we look at other areas, there is overlap with other areas, but there's a lot of differences as well. So of course, machine learning overlaps with statistics, with AI, even with computer science theory and so forth. But it is different. Statistics usually is about describing the world, about describing the data. So statistics is very good at taking a set of data and coming up with some ways to characterize it, but it's not usually focused on trying to predict new things. Although some people would say this is statistics. Generally, statistics is about descriptions. It's less about predictions. Machine learning is much more about trying to predict and trying to find new outputs or new novel, I would say, insights given the data that you have. So that's a major difference between, again, the goals of statistics and the goals of machine learning, although machine learning relies heavily on statistics. AI is, at least in theory, when people talk about AI, is this idea of trying to come up with ways that mimic human intelligence or other intelligence. Now, some of the machine learning methods we use, including neural networks, are exactly that. They are trying to use ideas from the brain to improve the accuracy of some methods. But most of the machine learning methods have nothing to do with human intelligence. For example, support vector machine, right? It's a great method. We will talk about it. It works very well in many cases. And nobody claims that humans or any other intelligent organism is using support vector machine. But the computer can use it, so why shouldn't we use it? So machine learning is less focused on mimicking or trying to be similar to other intelligent systems or organisms. It's more about trying to generalize from data. The way you generalize from data is not important as long as it achieves the goal that you define. And the goals differ by the task, but machine learning is not about trying to have an artificial intelligent agent, okay? That's different. I mean, there is overlap, but it's definitely not the same. Data mining is more about patterns, and again, you can extract patterns, but the question is, what do you do with them? So this is more a descriptive area rather than a predictive area. Data science is something that people use to talk about a lot of things. Some of them may refer to machine learning, some may be just combination of other things. So yeah, that's also definitely not the same as machine learning, okay? So again, there is a lot of overlap, and as I said, machine learning relies on foundations related to statistics and computer science and all of other things, but it also has unique aspects that, first of all, make it suitable for a department, at least that's what we think, but also make it suitable to be considered as a standalone field, which is why we have this introduction to machine learning and why we have programs in machine learning. And again, nowadays, I think it's much easier to convince people. When this class was taught, whoever taught it 20 years ago, maybe they had a harder time convincing them, but hopefully everybody agrees that machine learning is an important standalone area. Okay, so this is about trying to motivate why we think machine learning is an area on its own, and it has its own principles, its own set of goals and guidelines. And now if we agree, then we need to try and focus on what are these underlying ideas that machine learning is using, and how can we use them, or what cases can we use them in order to improve our understanding of various systems of the world and so forth. So before we go into a more generalized or more, I would say, theoretical issues, let's talk about some examples of machine learning and see what we mean by this generalization in practice. How does this ability to generalize from data affect us in practice? And, you know, what are the examples of some things that we do in machine learning? So an example that has been actually something that people have been expanding, and this started 12, 13 years ago, but it's actually gaining a lot of traction now, is trying to decode your thoughts using machine learning. So people, including people at CMU, basically are able to look at your brain scan and try to predict what you are thinking. And sometimes they can predict it even better than what you know that you are thinking, right? So this was an example of trying to predict some text that you're thinking about. But nowadays, brain scans are used for commercial, to evaluate commercials. So people are, so groups of individuals are actually wired to some brain scan devices, and they are shown commercials, and based on their activity, brain activity, the agency decides whether this commercial is effective or not, even if these individuals can't say exactly what they like and what they didn't like. So this type of things is gaining traction. Whether you like it or not is a separate issue, but there's a lot of interest and a lot of people working in that direction. So this is really understanding our own thoughts. And this is something on supervised learning. Stock market, we have been losing faculty over the years to various hedge funds, and one of the reasons is that because they think that you can use machine learning to predict regression. This is called regression, but to predict the values of certain entities. You know, I'm not sure this works or not. Didn't work for me. I'm still a paid employee, but maybe for others this can work much better. Right, so this is supervised learning, but it's a regression model rather than classification. So I'm not trying to predict yes or no. I might try to predict some continuous value. All the internet, a lot of the internet is organized using specific algorithms, but some of the ways things are organized is using machine learning. For example, those who use Google News, they see that Google is able to group news as they come into different types of stories. The way Google is doing that is using machine learning, specifically using clustering, because, right? I mean, it's not a human that sits and says this story goes to this part and this story goes to this subject. It actually has a way of clustering, grouping together things based on the data that it gets. So this is usually unsupervised, although sometimes supervised learning. Yeah, so spam filtering is also something that you know, you don't even know, I guess, but if you, or maybe you don't even mind, but if you go to your email mailbox, you have this spam folder, and the spam folder is primarily based on classification methods, based on machine learning.
Sorry, Ziv, it looks like we do have a question from Leonardo. Leonardo, do you want to just unmute yourself and ask your question?
Great, yeah, I will be more than happy to hear it.
Yeah, sure. So when you talked about machine learning being used in kind of like the receptivity of like commercials or the design of a news article, it seems like that's like a very open-ended thing. Like, how would you know what aspects of that commercial triggered a certain thing? Maybe there was something in the background. Maybe it was the tone of the commentator's voice. How would you narrow down to try to optimize that commercial if the search space is so large?
Yeah, so that's a great question. So again, so this becomes so a commercial, for example, the brain scan issue is something called supervised learning. Supervised learning means that you have some examples of things that you think work, and based on that, you are trying to predict new things. Just as an example, let's say, and this is something that is being used. Let's say that you have a political candidate that you want to come up with a good commercial for, okay? So you take some of these candidate supporters, okay? And you know, or you expect that they will react positively to this candidate, right? So when you show them the commercial, you look at their response and you say, oh, this is a positive response. Then you maybe take some of its, you know, the people who are against this candidate, and you record them and you see negative response. And now you take a group of individuals, and when you record them, which are, let's say, independent, you can say which things are positive and in which cases they seem more like the positive and in which cases they seem more like the negative. So I agree. But again, this is tricky. I mean, coming up, or I didn't mention it, we will talk about it later, but coming up with good data sets for training is one of the most challenging, if not the most challenging aspect of machine learning. And one of the reasons why neural networks, and I started by saying neural networks are so successful, one of the reasons why neural networks are so successful is because they do not need vast amounts of labeled data. They can actually use something called unlabeled data. So, you know, if we don't know the answer, we can take a lot of information, but we can't really use it to build a classifier. It turns out that neural network can actually use, that's why one of the reasons they're so successful. But getting a good labeled data set, a good data where you know the answer, is extremely hard. I agree, but you know, sometimes you can do it. Okay, the next example I wanted to talk about is something that I mentioned about generalization, something called never-ending learning. This is something that, you know, this is from 2017, but it has been going for, I would say, at least 5 years, maybe close to a decade at CMU. Basically, this is an agent that crawls the web and tries to learn every day some new things from the web. So basically, it takes a sentence, it tries to do some NLP analysis, and every day it adds to its knowledge base more and more and tries to generalize the information. So this is called NEL. Obviously, one of the things that people are very excited about and very familiar with is autonomous driving. And autonomous driving nowadays, right, is something that you know, people, I would say, so I taught 701, I think 2 or 3 years ago, and I said then that I don't think my kids, which were then I guess my daughter was then 15 or 14. I'm not sure she would need the driver license. I said that 3 years ago because I said, look, I mean, everything is moving to autonomous vehicles. Unfortunately, my daughter is almost finishing her driver license, and we'll see how the car survives. But so I was wrong. So it took definitely. I mean, in 2017 we thought autonomous driving is around the corner. We were wrong, and now it's 2020. We still believe that autonomous driving is around the corner, but it may take long, or it's much harder than people thought, at least a few years ago. But still, it's not like we can't do it. So even 10 or 15 years ago, CMU, or maybe 13 years ago, CMU was able to demonstrate that a self-driving car can ride within a city, but with relatively small number of individuals and relatively small number of other cars. So this is a very limited experiment, but still, this is something that machine learning could achieve, and hopefully going forward will become much more doable, maybe with some of you, when some of you graduate and then join the companies that are trying to do it. So this is definitely a major task of machine learning, which hopefully will come to completion soon. Another thing that people may or may not realize is using machine learning is Google Translate. So, if you have been to some a foreign country over the last few years, for example, if you went to China, it's very hard to communicate, or at least for people who don't know the language. But Google Translate now and other translation are doing an incredibly good job at translating language. And most of the newer translational methods are using neural networks, specifically something called recurrent neural network, but they're based on machine learning model. And that's a big revolution. In fact, until 4 or 5 years ago, Google Translate has been around for a long time, but until 4 or 5 years ago, it was mainly based on a standard natural language processing model, which was very manually annotated. And nowadays, or at least a few years ago, it moved to a neural network based. And of course, as I said, this requires a lot of training data. So they had a lot of samples of good translation that humans did. But once you train on that, you can build an automated translator that is doing pretty well. And again, I don't know about Chinese. Maybe there are some Chinese students in the class. Hopefully the translation they see here makes sense to them about the class description. But anyway, this is something that is using machine learning. I always like to say, just because that's an area I work on, that machine learning is also something that not just human use, or not just neural networks are something that we can learn from nature. So there are other things we can learn from nature. And recently, work in our group has shown that bacteria cells, so these tiny cells that we actually have in our body, a lot of bacteria cells, but some of them are also disease-causing pathogens. But bacteria cells basically use something similar to Boolean propagation, which is, or to methods that are similar to joint probability distribution estimations in machine learning, in order to find the best way to navigate a collision course or a maze, basically, to get to the food. So this is also one way that machine learning is being used, of course, not by design, but or not by some generated algorithm, but in practice. And this is something that we can use if you think about it, for example, for robotic applications, where you also have a set of agents that need to navigate a complicated environment. But this is another example of, I would say, intersection between artificial intelligence, because this is intelligence, at least one way to think about it, and machine learning. Machine learning is also being extremely popular and useful in biology, which is, as I said, my area. For example, this is a subset, very small subset of your DNA, and this basically has a set of letters, A, C, G, and T. This is the letters that the DNA is composed of. And one question that we have is, what are the punctuation marks and what are the parts of this sequence, right? It's just looking at this, that's what we see when we do sequencing. And in order to determine what is the gene, what are control areas and so forth, we use a lot of machine learning methods, a lot of methods related to hidden Markov models, which have been very popular, but also other types of methods. Nowadays, neural networks are also being very successfully used to understand our biology and genome. and many more. There's one video I love to show, not because it's very sophisticated machine learning, but it's a very cool video. So let me see if I can show it and then talk a bit about what the video shows. So people see this is a helicopter. Of course, autonomous helicopter, so this is pretty small, but it can fly very nicely, and it can actually fly upside down and do some very interesting maneuvering, as you will see in a second. Yeah, so it can go, you know, it can flip back and forth, and there's no human controller, so the helicopter is doing this all on its own. Now, of course, you can control it like a drone, but in this case, this is fully automated. And the interesting thing about this, yeah, I really like the video. We'll have to stop it, unfortunately. But anyway, the cool thing about this is that the helicopter was trained not using some example data, like we said, like showing some or taking some helicopters that crashed and didn't crash and training based on that, because you need negative examples and positive examples, but rather it was trained using something called reinforcement learning, which is a fully, or something can be done fully theoretically in a computer, and teach the helicopter before it even flies, right? So if you have a reasonable model of how a helicopter flies, you can do something called reinforcement learning. Each time it crashes, it learns that that's not a good end goal. So you basically backtrack and see how you can correct what you did. And each time you successfully finish the maneuver, you get some rewards. And so as the training continues, you improve and improve your model until you can actually do these maneuvers on your own. So this was trained in the simulator, or the model was learned using a reinforcement learning simulator. And then when the helicopter actually took to the sky, it was able to do these maneuvers almost, almost perfectly without any need for a training data, or without any need for some crashes for it to work. So this is called reinforcement learning. And again, we will discuss a little bit of reinforcement learning in this class. Okay, and as I said, many more. Medical informatics nowadays is becoming very important. Social networks rely more and more on machine learning. Of course, all the commercial, or all the ads that you see in your Facebook feed, or when you watch YouTube video or whatever, are tailored to your own characteristics using machine learning methods. And there, the challenges are slightly different than what we usually talk about, because you also want something that works very fast, but this is all based on machine learning. So machine learning is, really all around us. It's not just something we just discuss in classes and lectures, but something that people rely on all the time. It's all around you. You use it all the time, and hopefully or likely this will be more and more useful going forward. Okay, so this is just some examples. Let's go a bit more into, so as I said, I mean, biology and all of other things. Let's go a bit more into specific aspects within machine learning research. So there's three major things we focus on when we talk about machine learning, or that we need to focus on. One is the data. The other is the algorithms, and the third is something we call tasks. So different algorithms, or some algorithms, can be applied to multiple tasks, okay? And the definition will become clear hopefully soon. One thing I want to say is that in this class, we primarily focus on the second part of these three axes, the algorithms. That's what we usually focus on in Introduction to Machine Learning. I do have to say, and I think I'll emphasize it in future lectures as well, that data may be more important than the algorithm. So sometimes if you have better data, almost any algorithm will work well. And if your data is lousy, then even the most sophisticated algorithm will not work well. Similarly, if you have ways to process your data, to prepare your data to being analyzed, it might be much more important than the actual algorithm you're going to use, okay? Unfortunately, or no, or I don't know if it's unfortunate, we usually don't talk too much about it in introduction to machine learning. One of the reasons is because it's much harder to generalize this. It really is very domain specific. For example, in biology, you need to do one thing to process the data. If you have housing data and you want to predict house prices, you may need to do something very different. It's much harder to generalize this, whereas algorithms are much more general. So we usually focus on the algorithms, but you definitely should realize if you have a real world problem, the first thing you need to pay attention to is the data and how to process it and how to represent it, okay? It's not trivial. Think about cases where you have categorical data, continuous data, discrete data, and you want to put all of them into a model. How do you do that? That's not, we will talk a little bit about it, but this is a broader area. As I said, algorithms are the thing we'll focus about the most, and tasks are related to algorithms and basically represents the goals of the operation. Sometimes different algorithms can be applied to the same algorithm can be applied to multiple tasks. For example, you can use one algorithm for regression, so getting a continuous value, and the same algorithm for classification, getting a discrete value, but with a small change. So there is no, it's not a one-to-one division between algorithms and tasks. Some algorithms may be appropriate for multiple tasks, and obviously one task can have a lot of different algorithms that can work. Okay, so data just more generally, right? So if we can have a lot of different types of data. We can have something called fully observed, so we see all the observations, but we can have, in many cases, partially observed. For example, if you want to predict house prices, and there was a big competition recently by a company called Zillow that tried to ask users to improve their predictions. So you can see that sometimes you have all the information for the house, but sometimes you don't have all the information. So for example, you don't know, I don't know, how many windows the house has, or what year it was renovated and stuff like that. So sometimes you have something called partially observed data, and you need to fill in or somehow ignore the missing parts. And the question is, how do you do that? That's not a trivial. There could be other issues related to the data. As I said, some data can be of different types: discrete, continuous, categorical, and so forth. So this is the first thing. The other thing, which we are not going to talk about in this class, although it's an important area in machine learning, is something called active learning. So usually in this class, or I would say for almost all of this class, we would assume that your goal is to generalize from the data that you are given to an algorithm. Okay, so I'm giving you a set of data, either labeled or unlabeled, and you need to supervise and you need to generalize. But that's not the only way to work with data, right? Another way to work with data is to ask for more data. You can say, look, I can't generalize from the data you gave me, I need more data. Or I can't generalize very well, I need more data. We usually do not assume that that's an option in this class, but in machine learning, there is an area called active learning where you're actually allowed to ask for more data, and not just to ask for more data, but to specifically ask for labels or information about specific samples. So this is called active learning, and it relates to how we basically collect or analyze data. Again, we won't talk much about it in this class, but this is an important area of machine learning. So this is data, as I said, unfortunately, or maybe not the major focus of this class. The second part, which is the major focus, is related to algorithms. And algorithms, we divide algorithms along different lines, along different categories. We are going to have some algorithms that are probabilistic, some are algorithms that are that have parameters, some algorithms that don't have parameters, so non-parametric, parametric, discriminative algorithms that don't use probabilities, just divide the two areas. So there were going to be lots of different types of algorithms, and we will try, when we present an algorithm, to say which type. So for example, naive Bayes is a probabilistic model, whereas I don't know, logistic regression is a parametric model, and because it has parameters, and k-nearest neighbor is a non-parametric. So for each one, we will try to specify its characteristics, but we are going to have or we will be able to assign different, or we will assign different characteristics to different algorithms, okay? It could be that different algorithms like probabilistic and discriminative, which is not probabilistic, are trying to solve the same problem. It's not necessarily that probabilistic algorithms are only good for one task and other algorithms are good for another task, okay? So there's going to be a lot of options to do, or a lot of different algorithms that can work on a lot of different tasks. Okay, so the basic idea of machine learning, as we said, is going from data to a model to use a learning algorithm and then extract knowledge. The way we do it is we have some way of learning a model from the data, okay? And the model can be parametric, non-parametric, it will be a lot of different things. And once we have the model, we can use it to make inference. What does it mean to make inference? Inference could be that if we have a new sample that we never seen before, we want to predict what it's going to be, or maybe we want to generate something new that was never saw before, and use that, or maybe we want to determine some probability of an event, and so this is called inference. Okay, so the goal of the model is to summarize the data. Okay, so basically to get a really concise representation, as concise as possible, of the data without losing a lot of information. So if you have 1,000 values and you can summarize all of them with 2 values, maybe the mean and the variance, that's a much better representation than the original set of values. So on the one hand, the model is a summary of the data, which is like statistics is handling it. On the other hand, the model can be used to generate new instances in some cases, okay? And to explain how they will generate. So this is the model itself. The model is a way to somehow describe the data in an efficient manner. But then the next step is inference. How do we use the model to make the predictions? And this is where we said machine learning basically differs from other areas. Because machine learning doesn't care just about describing the world, but also how to use that description to predict new events or to be able to predict new outcomes. A bit more formally, so we have parametric models. Parametric models basically means that it doesn't matter how much data you give it, the model size stays the same. For example, let's say we want to fit a regression. In this case, let's say a blue, which is linear regression, or maybe a quadratic, a polynomial, a second-degree polynomial to the data. And we have some samples here, right? It doesn't matter how many points we get, the model that we will learn, the parameters that we will have are the same, right? For a linear line, we will have 2 parameters. For a second-degree polynomial, we'll have 3 parameters, and so forth. The model, the model we learn always stays the same. Okay, so this is called parametric model, and it's nice because it's fixed based on the number of parameters, the number of values we need to keep is fixed. The challenge is that maybe we don't keep enough, and then we don't make the ultimate use of the data. Okay, but that's definitely, or most of the models we'll talk about are parametric models. There are also methods that use something called non-parametric models. Non-parametric models grow with the data. So basically, we don't try to keep any summary of the data. Here, we use the polynomials to summarize the data, right? If we get new points, we just update the values of the coefficients of the polynomial. In other models, for example, in something called decay nearest neighbors, we don't have a model of the data. We use all of the, when we want to learn something from the data, we use all of the points we have seen so far. So if you give me more points, the model grows because I'm using all the points. Okay, this is called non-parametric models. And of course, if we have more data, the complexity or the time we need in order to decide becomes greater, right? So it grows with the data that we have. Discriminative models are models where we just want to find a discriminant between 2 classes, for example, or 3 classes. So we don't really care about how the data was generated. The only thing we want to know is where does this point lie with respect to a line or a plane that separates them, right? So if we want to just classify or determine if a point is black or white, then we can just find a line and say anything above on one side of the line is black, anything on the other side is white, and this is the 2 classes that we have. We don't really care, right? If you want to create a new white point, I don't know how to do it. I don't know if a new white point should go here or should go here or should go here or should go here. The model doesn't tell me. But if you give me a value on this two-dimensional space, I can tell you whether I think it's black or white, depending on the line, right? If this is the line, then I would say things here. If this is, I mean, you have to come up with the line. This is a parametric model because in this case, for example, we have a line which is parameterized by, in this case, you know, two values. You can have higher dimension, but the model itself is discriminative. It doesn't tell me anything about how to generate things. It just tells me about how to distinguish between two things. There's also something called probabilistic model, which I'm not showing, where you can actually generate new instances. Okay, so this is, again, these are just a few examples. There's more ways to define algorithms based on parametric, non-parametric, probabilistic, discriminative, and others. Okay, so this is algorithms. The third thing is the task. So what do we want to do with this algorithm? What's the goal? What's the inference goal of the algorithm? As we said, machine learning can be divided into, I would say, four main tasks. The first, and the thing that we will probably spend most of the time on in this class, maybe between a third and half, is something called supervised learning. Supervised learning is the case where the task is to make predictions, either continuous or discrete, given some inputs for which we have the known labels. For example, I can tell you if this is a cat or a dog based on some images, and now I give you a new image and you want to predict whether it's cat or a dog. Or I can tell you the stock price for tomorrow for a specific stock, and I want you to predict the stock for, I don't know, 2 days from now if I give you all the information from a few days before. Okay, so this is, the goal is to estimate an output given an input, and this is usually called, or not, this is supervised learning or prediction problems. And there's two main directions, right? One is, as we said, it's a discrete case where you want to predict a label. For example, you want to classify documents into sports documents, news documents, science documents, where the label is a discrete entity, like, you know, 1, 2, or 3. Or maybe you want to predict a continuous value, for example, stock price. Okay, so given X, you would like to predict Y, right? So we said classification, right? And lots of classification problems, text classification, image classification, sound classification, and so forth. So this is definitely one of the, right, this is definitely one of the major goals, or maybe ad classification, which ad you would like the most, or so forth. So this is classification problem. And the second problem is regression, right? As I said, stock market, or maybe you want to determine what level of the, or how much of a drug you should give an individual based on their gene composition. That's also a regression problem, right? So like some quantity of the drug that you want. And again, in both of these cases, regression and classification, we assume that the training data includes the samples and the labels, right? So in the classification case, we have the samples and the class, and in the regression case, we have the samples and the expected outcome of those predictions. Some problems are much more complicated. So some problems are very simple, classification, either regression or classification. Some problems mix the two, right? So if you want to do something like face detection, maybe you want to determine whether this is a specific individual or whether this is a face, or give some continuous value about whether this is a face. Similarly, in autonomous cars, right? So on the one hand, you need to make predictions about whether you're too close to another car, because if you're too close, you need to put the brakes, but you also want to have continuous predictions about how far you are from a specific traffic light, how likely you are to get to the intersection before the light changes, and so forth. So most of the real world problems involve a combination of discrete and continuous predictions. And also a combination of input data, so discrete and continuous data. Okay, so in real practice. So this is, as I said, this is mainly supervised learning. So supervised learning is about prediction. Another part of, or another set of problems is more about description rather than prediction, and this is something we usually call unsupervised learning. And unsupervised learning includes something called density estimation, so trying to predict some probabilities from a data. For example, what's the probability that if we take the students in this class, we will find someone who is 6'2", tall, or maybe someone who is 5 foot tall, right? So these are probabilities related to height of students in the class. So this is called density estimation. We can use it for clustering. We already talked about clustering, for example, grouping documents based on what the topic is. Dimensionality reduction. So if we take things in very high dimensional space, how do we represent it in a low dimensional space? For example, pictures of individuals, how do we put them in a space that we can see? This is called unsupervised learning, and the main difference between supervised and unsupervised is that in this case, we don't get the labels, we only get the samples. Okay, so here's an example. We have, we have some population density in the US, and we want to predict if someone comes, what's the probability that they are from Pittsburgh, for example. Okay, so for that, we need to compute the probability of individuals and how many we have and so forth. And based on that, we can predict what's the probability that someone is from Pittsburgh. So this is density estimation. Another thing is unsupervised, which is clustering, right? We take all the documents, and based on the words in the documents, for example, we want to group them into different topics. We don't know what the topics are because nobody told us what the topics are going to be, but we can actually find these groupings just based on similarity of words between documents. So this is called clustering. You can do it for documents, you can do it for images, you can do it for genes in the body, you can do it for a lot of other things. Right, you can do, this is an example of clustering images. Even if you don't know what the image means, once you cluster it together, it groups into cases, for example, sunsets, outdoors, and so forth, which you can identify even if you don't. And you can also cluster web pages and so forth. The last thing in unsupervised learning is something called dimensionality reduction. If you want to represent high dimensional spaces in 2 dimensions, maybe because it's easier for you to visualize it, or maybe it's easier to work on it, then the question is, how do you put different facial expression of the same individual such that things that are very close in the high dimensional space are close in the low dimensional space, and things that are far away in the high dimensional space will stay far away in the low dimensional space. And it's not always trivial. It doesn't necessarily follow the transitive requirement and so forth. So density or embedding or dimensionality reduction is a major issue. And there's actually a lot of interesting work recently, mainly, and this is definitely an area that receives a lot of attention because a lot of the data that we are dealing with now is very high dimension, including image, of course, image data, but also a lot of data in health, in biology, and so on. Okay, so this is the major directions in machine learning. Just to summarize, right, we said we have supervised learning where we are given a set of features and labels. Features are the input samples, labels can be continuous or discrete, and the goal is to predict the outcome based on the input data. Unsupervised learning, mainly some related to description, not prediction. And the goal is to discover some patterns in the data, so similar things in the clustering case, or dimensionality reduction to put things that are close together in high dimensional space. Two other things that we haven't discussed much, but we will discuss in the class is something called reasoning under uncertainty. So how can we learn a model of the world from samples, right? So if a robot goes in some cave and it wants to learn the dimensions of the cave and the structure of the cave, is there any way for the robot to map it as it goes, right? So every time it bumps into a wall, it wants to learn that this direction is not good for you. But maybe at some stage, if you don't take a left, you would miss an important turn. So you have to come out somehow balance between negative examples that you've seen and things that you haven't seen, and try to improve your understanding of the world as you go. This is called, or one of the ways to do it is called reinforcement learning, and this Markov decision process and so forth. And this is another area where we do machine learning. And the last part I mentioned, we wouldn't probably have a lecture on it, but it's an important area of machine learning, is called active learning. And active learning, unlike all the other methods we talked about, the goal is not just to select the algorithm or learn the algorithm, but it's also to determine what data is the best to learn an optimal algorithm. Okay, so this is called active learning. And active means that, right, you have to actively ask for the data. A bit more formally, okay, so we should at least end with some formalism, because machine learning from now, I mean, except for this lecture, we will be much more formal going forward. So in supervised learning, we have X and Y, and the goal is to learn a function from X to Y, where Y is the label and X are the samples. Okay, so we can have images where X is the pixels and Y is the label, cats or dogs, or we can have stock values and Y is the prediction for the next day. Okay, so this is called supervised learning. In unsupervised learning, we have the same inputs, but we don't have the Y's. Okay, so we don't get the labels, we just get X. And the goal is to group these X's into different groups, or to reduce them into a dimension where you place each of these X's on its location. So this is unsupervised. In reinforcement learning or reasoning under uncertainty, we add to the observation something that is called a reward. So we are in a specific place. So this is the environment. The reward is, maybe you can think of it as the Y, but in addition, there are actions. There are things we can do. So you can turn left or turn right, and you want a function that maps the environment and actions, the environment and rewards to your action. This is called the policy. So if you know what the environment and the reward is, you want to know what is the next action, or what is the next step we should take. This is the goal of reinforcement learning. And active learning usually start with XY, so XY pairs, which are the labeled data, and a set of unlabeled data. And the goal is to select another subset of the unlabeled data, which the user will label for you. So you tell some oracle or some user that, okay, you gave me these examples. I also want to know the labels for some of the others. For example, if I give you all the images on the internet, and for some of them I give you labels, and for most of them I cannot give you labels, your goal is to select a small subset of the unlabeled images and ask for labels in order to improve your classifier the most. And of course, the question is, what is the best subset for you to ask for? Because you can only ask for another 100, and which one of these will most improve your classifier? Okay, so this is unsupervised learning. Good, and I think we are done for this lecture. Right, so yeah, so as I said, this is this is introduction. I've been a bit less formal, but going forward, we will actually use math and mathematical notations much more. Any questions about the introduction? Daniel, is there any other things we didn't discuss in the chat?
No one had their hand up. It did look like Arun just asked about, he said, is the policy dependent on the reward after learning, because you don't always know the reward a priori?
Right, so that's a great question, and that depends on the model. In some models, we know the model in advance, so we know the rewards, and we just want to learn the policy. But as you said, in lots of real-world applications, we don't know. So we know what actions we can take, but we don't really know the rewards. So reinforcement learning allows you to learn both the policy and the expected rewards as part of the algorithm. So you don't need to assume that you know what are the rewards. You learn you try to learn a model of the rewards as part of the algorithm as well. And again, we'll get to that when we talk about reinforcement learning. Okay, good. So if there's no other question, as I said, we will meet back on Wednesday. We will meet back on Wednesday, and we are going to have the first recitation on Friday. The first problem set is only going to be out next Wednesday. So you still have a bit of time without any problem sets. But I definitely encourage you to attend the recitation, even if we don't have a problem set, especially those who have, I mean, the recitation will mainly be on background material and probability and statistics in Python. So if you feel that these are things that you would like some refresher on, and we'll discuss this very briefly next time, but very, very briefly. So if you want a bit more, you should definitely attend the recitation. And as I said, that's it. If you have anything else, you can email Daniel and me, or post a question on Piazza, which is the best, because that's something that others can see as well. And we'll be more than happy to talk to you. Okay, so yeah, we'll see everybody again on Wednesday. Oh, by the one last thing. On Wednesday, I'm going to start using Piazza for quizzes. So please be ready with Piazza open. The quizzes are not graded, but it's something that I'm using during the class. So please have Piazza ready for Wednesday. Okay, I'll see you. Bye.